It has been a pretty full week and a lot of discussions. So difficult to conclude and wrap up. I'm not going to try to summarize any of this very full numerous discussion. I'm just going to try. Is it better? Basically, I will, from this position of PI, saying where do we stand and where should we go in the year and a half to go before the next release and the next release of papers. In cosmology, in fact, the gain comes from the previous experiments, from the better sensitivity, but even more from the angular resolution. We get more acoustic peaks, and the lensing. And that's what helps resolving a number of CMB degeneracies of the previous experiments. We had also the better component separation, which was allowed by the very broad frequency range of Planck. And, as was recalled, a lot of galactic physics, in fact, came out. It was not in the cosmology, but a lot of galactic physics will come out. And especially the first polarization papers, you saw some view of what's going to come in the next few weeks, will open a new era, for example, in mapping the magnetic field. But the next step, which will be the use of polarization, will really make full use of the sensitivity we have, that which has not really been done so far. And that will broaden, obviously, the consistency checks we can have, especially when we look at broader models and the CDM, and when we look at all the tensions, discrepancies, anomalies, name it the way you like. We had promised, in fact, when we proposed Planck, to try to build an experiment which will be limited by our ability to understand the foreground. It was mentioned several times that we are basically there, although, and that's plots from the likelihood paper, which shows the CMB, and on the log scale here, the foreground, and especially at IL, you could see all these foregrounds for the 143 and for the 217, is a best model of both the cosmology and the CMB. And some of these, if you read the paper in detail, you will see that they were pinned down well enough not to affect the cosmology, but there are some tensions between these, some depending exactly what the models and the complementary set of data you are using. Basically, you could see some power jumping from the point sources to the correlated CIB, or from the CIB to the SZ. And I certainly believe that we can do a better work on that, and we will certainly do. Just examples of that. That's one image you have not seen, or I think you have not, because the CIB paper was not presented here, but it will be in the set of papers to come. And that basically is a large area for which the CIB has been extracted and separated from the dust. And people might well ask, how well do we know and why do we know that we have really separated the high galactic dust from the CIB? And we have an answer that we have not fully exploited, which will give an illustration of what I think we can do in the future on component separation, which is the paper, which is the correlation between the lensing and the peak of the CIB. And that was the stacking that that were shown by Olivier Doré, where we see the peak of the infrared map and the lensing of the mass, which is associated with the star formation. Now, what we have not done is to use fully the complement of what story that is telling us together with the direct detection of the CIB, for example. So that's one thing that we will exploit in the coming months. My second example will be in polarization. the CMB polarization at low L will bring a very critical test on the single field inflation, as we heard many times, looking for the tensor mode. And I think, from what I heard and I understand from the theoreticians are saying, either we will detect them or we'll put a very significant upper limit on that if we succeed to get to the sensitivity limited by the noise and not by the systematics as it is now. So that's a very important part. But in fact, it will help on other things, in fact. Once again, the polarization will help us removing or checking some of the tensions and difficulties we have, and when we look at broader models than the lambda CDM, we are going to use that. And the second part is that polarization will help a lot also checking how well do we separate the component, because as was mentioned recently this afternoon, the polarized foregrounds are a small number compared to the intensity foregrounds. And so when we study the polarized foregrounds, we'll see how coherent it is with the polarized foreground. And the past has shown us that this was an important one. I don't resist showing that again. And I think I show that not only because it's a very interesting and very striking picture, but because historically, and that's to tell you about where we are and where we want to be next year, is that this image came out for the first time in the Planck data very early, just after the Komatsu paper, the WMAP paper, which did the first attempt at that, and it was quite striking. One of the young postdocs, in fact, in our group did that, and it was data that we thought were not really suitable for cosmology. Now, that was not clean or checked for many of the systematics we knew were in there. And so that reflects, this is a bit better now, but the image was not that different, in fact. When first time he showed them to me, basically what was said before by Marco, we had trouble to distinguish which was the simulation and which was the data. So it shows that the data, in a pretty rough and raw way in Planck, are extremely good. The point is that to do the cosmology we want to do with that, we need to clean the systematics to an incredible level that I've never seen in many experiments, and I've participated to a number of them. So that's an illustration. Let me just finish by going back to the consistency. Jean-Michel Lamar was mentioning that there are a number of things we were expecting to draw out of our test, ground test, and so on. And some of these, in fact, we extracted from the data and from the sky. And we are doing more and more of that. And you have seen a lot of this consistency in each spectral band between detectors, between spectral bands inside an instrument, and between the two instruments. And basically, we are going to play that game between Planck and WMAP, and probably later with ACT and SPT. And that's going to teach us also how well did we do that in Planck and in the other experiment. And so this consistency is an extremely powerful tool that we have used a lot, but we are going to use even much more in the future. So that's where I see now us going. Thank you.